Hey guys, welcome to the last set of videos we have to watch with me being gone. I will be back on March 5th, so we just got a few more to do, and we're going to work on chapter 6 and 17, which is thermochemistry. The nice thing is you've actually already done a little bit of this, so this shouldn't be too bad. But keep in mind this chapter is kind of an overload of information, and some of it can be very abstract, so this is going to require your full attention. And it's going to require you to read the book. The new book that you guys got this year actually does a pretty good job of breaking this chapter down and really working through the material. So please actually crack the book open, for some of you probably the first time all year, and actually look through the sections I tell you to in your calendar. And then those of you that took AP Bio, get the bad taste out of your mouth. Gibbs free energy, entropy, and entropy are not that bad. They were a little bit rough in AP Bio because you didn't have the chemistry background. You now have the chemistry background, so let's dive through and kind of see what we have here. The first thing I want to do is talk about what we've already talked about, or discuss what we've already talked about, which is that little heating curve we did in the last chapter, if you remember, where... So remember down here we have solid, we have the melting process, our delta H of fusion right here. We have the liquid and the boiling process, which is delta H of vaporization. And of course we have the gas phase. So let's kind of talk a little bit about what's going on here. And this is stuff we've already discussed. So down here we're heating the solid phase of the substance. So we're going from a solid to a solid, essentially, from point A to point B. So if this is just going from a solid to solid, what's actually happening here? Well, the molecules are moving faster as we increase temperature. Well, what does that mean, molecules are moving faster? So let's go back to our Maxwell-Boltzmann curve, which remember was talking about speed, our average speed, okay, which was something like that. Well, what controlled the average speed of a substance? Well, it was the average kinetic energy, which is not equal to, but remember, related to temperature, okay? So as we're increasing temperature here, we're increasing the average kinetic energy, therefore we're increasing the speed. So what's actually changing here in terms of energy between point A and point B is the kinetic energy, okay? Well, what's happening from point B to point C? Well, this is where we have the melting process, which is where we have IMFs breaking. Okay, well, what's actually going on? What does this mean? So I don't know if we've talked about this yet or not, but water is attracted to another water through this intermolecular force, which is the attraction between the partial negative of the oxygen and the partial positive of the hydrogen. Remember, this is our hydrogen bond. This right here actually contains potential energy, okay? And we're going to talk a lot more about this as we go through. But when we are talking about bonds breaking, and that means any type of attraction in terms of Coulomb's law, so that can be an inter or an intramolecular bond, and again, we're going to talk about this in more depth a lot later. But what I want you to recognize is that this force of attraction is potential energy, or contains potential energy. And in actuality, it's really the lack of potential energy, which does not make a lot of sense, but let me see if I can break that down for you. So what I want you to do is take a notebook, and I want you to hold it in the air. Okay, so let's say this is our notebook in the air. And what I want you to do is drop it to the ground. Okay, well, what just happened? Well, it had a lot of potential energy here, or it had a high amount of potential energy. When you dropped it, it released that potential energy, so it now has lower potential energy. Potential energy is actually, in essence, the instability of an object. The more potential energy it has, the more unstable it is. Versus the less potential energy it has, the more stable it is. So this force of attraction actually is stabilizing these molecules, okay? Or even if we want to think about the bonds within the hydrogen and oxygen in water, also is stable, okay? And a technicality, this is more stable than the force of attraction here. Intra is more stable than inter. And that is going back to our Coulomb's law, which remember is the force of attraction is Q1, Q2 over radius squared. Remember, this is much shorter, has a much smaller radius, therefore has a much stronger force of attraction. The higher the force of attraction, the more stable it is, therefore the less potential energy it has. And we'll break that down further a little bit later. Don't let that stress you out too much, but I kind of want you to get this idea going on here. Is basically when we are dealing with B to C, we are basically playing with potential energy. Okay, and then from C to D, again, we're increasing temperature, so therefore we're messing with kinetic energy. Going from D to E, again, we're dealing with intermolecular forces, so we're dealing with potential energy again. And then, of course, E to F is dealing with kinetic energy. So when we take these steps and add them together, remember we were adding like Q1 plus Q2, etc., etc., etc. What we're really doing is looking at the total energy change of this process, which is looking at both kinetic and potential energy changes. And that, in essence, is what thermodynamics or thermochemistry is. It is looking at the energy change, the total energy change of a system. So it is looking at both potential and kinetic. Okay? So with that in mind, let's dive into this odd world of thermodynamics and see what we can come up with. Okay, first and foremost, some basic definitions. So we've already talked about potential kinetic energy and just general energy, but let's talk a little bit further and actually put some definitions to it. So energy is in the physics term, and keep in mind thermodynamics definitely starts treading into physics realm. If you decide to go into the chemistry field, you'll find out there is a chemistry called P-Chem, or physical chemistry, and this goes into a lot more depth than that. And also keep in mind, physics really requires calculus to solve their problems. We're not a calculus-based class, though keep in mind P-Chem, or physical chemistry, is a calculus-based class, so chemistry does have calculus in it, just not at this level, not on the Gen Chem level or the AP Chem level. So we are definitely treading into physics here. Okay, but we'll keep it on an algebra level, but that also means we will be making assumptions or simplifications to allow for our math to remain in the algebra side of things versus a calculus side of things. So energy is the capacity to do work or to produce heat. Now, work in essence means changing position or direction, or not changing direction, excuse me, changing distance, moving basically. In our world, for something to do work, we have to change pressure a lot of times because a piston in a cylinder would be moving up and down and therefore changing distance and therefore doing work, and pressure would also be changing. For our simplification, so we don't have to deal with calculus, we will not be working with pressure in any way, shape, or form for these problems. So what we're looking at is the production of heat in terms of energy. Remember, again, this is both kinetic energy and potential energy changes is what we're looking at. Because remember, these two are switching back and forth into each other. Okay, so what is potential energy? Potential energy is the energy due to position or composition. And again, we're not really looking at position so much. We are looking at composition, okay? And really stability in the simplest form here. Okay, and that stability comes from, again, looking at Coulomb's law. It's the distance and the strength of the bond. The stronger the bond typically means the shorter the distance, and that also means the more stable it is. The more stable it is, the less potential energy it has. So keep in mind there is an inverse relationship there. As stability goes up, potential energy is going to decrease. We actually want less potential energy. So again, remember, take your notebook, hold it up, drop it to the ground. Remember, up here it has a lot of potential energy, so high potential energy. Down here it has low potential energy, which positions more stable. The one that's on the ground, less potential energy. And keep in mind, it never really has zero potential energy. Okay, it is on the ground, but it could technically go further down. So keep in mind, it never really has zero potential energy, and that's going to play a role as we move into looking at bond energy a little bit later on. So just kind of remember that. Kinetic energy is the energy due to motion. So we do have our atoms and they're moving consistently. Remember, this is looking at kind of the change in temperature, if you will, because remember, average kinetic energy and temperature are related to each other, not equal, but related to each other. So as temperature changes, kinetic energy changes, or as kinetic energy changes, temperature changes. So this is really important. So how do we measure if there's an energy change? We can't measure potential energy. There's no way to. We don't have an equipment to do that. So what do? We measure the change in kinetic energy. So kinetic energy is going to turn into potential energy is going to turn into kinetic energy. So if temperature is increasing, that means we are gaining kinetic energy. That kinetic energy had to come from somewhere. It came from potential energy turning into kinetic energy. Same idea, if temperature is decreasing, we lost kinetic energy. Well, that kinetic energy has to go somewhere. It's going into potential energy. And of course, that is an oversimplification. So keep in mind, energy can be transferred outside of the system, but we are ignoring that fact in order to keep our math simplified. So we're just kind of dealing with this interchange between potential and kinetic into potential, and ignoring the fact that energy can be lost to the surroundings in that regard. Of course, temperature, again, we've already discussed, is the motion of particles, and that is our kinetic energy. And of course, remember, that is an average kinetic energy to think back to what we've discussed in our gas laws. Okay? From there, we have heat, okay, which is the transfer of energy between two objects. This is commonly dealing with kinetic energy because, again, that's what we can measure. But keep in mind, it is also looking at both potential and kinetic energy. But it's just looking at that transfer of energy between two objects, measuring kinetic energy, but remembering that kinetic energy had to go or come from somewhere, which is our potential energy. So potential energy is kind of tied into this mix as well. Right? State function is probably a term you haven't heard before. So you've heard of energy, kinetic, potential, temperature, heat, all that fun stuff. State function is probably one of those terms that you've never heard of before. So what is a state function or state property? Basically, it is some type of property that is dependent on the state, not the path it takes to get there. So what in the heck does that mean? Let's kind of do a very simple example here. And your book does this example of distance versus elevation. So what I want you to think about is you are climbing the Appalachian. So you're climbing a mountain on the Appalachian. Okay? And there's two different pathways you could take to get to the top. Okay, you could take one that is very, very steep, but shorter, or you could take one that's very, very long, but a lot more shallow, or a lot less steep, if you will. So you could do either path. Does it really matter which path you take? No, not really. If you take the long trail that's not as steep, you're not going to be using as much energy in terms of having to move upwards because you're moving at a shallower level, but you're moving farther, so you're still using a lot of energy. Okay, versus moving on the shorter trail, you're using a lot more energy in terms of fighting gravity, but you're not traveling as far. So it's kind of that 6 of one, half dozen of another. You're using probably the same amount of energy in both cases to go from the bottom of the mountain to the top of the mountain. Therefore, it doesn't matter which path you take. Your amount of energy either way is going to be the same. That's what we're referring to. And we're going to be dealing with a lot of change in energy for reactions. And the reaction could go one direction or another direction, but the amount of energy change is exactly the same due to the fact that it's going from one state to another. And state could be state of matter. It could be chemical formula. And it could be a couple of different things. The fact that it's dissolving. So state does not mean state of matter alone. It basically means what it is in the simplest terms there. Okay, and we'll go into that a lot more as we move through this material, as we talk about enthalpy a little bit further, entropy, and Gibbs free energy. Those are all considered state functions. So we'll kind of give a little bit better examples that will probably make a little bit more sense. But right now, kind of keep the idea of climbing a mountain. And again, two different pathways. Both pathways get you to the same point, starting at the same point. And you're basically using the same amount of energy. Okay, so that's it for the original or the initial intro into thermodynamics. I'm going to stop here and then we'll move on. Thanks, guys.